All right, so remember when I said that if you had a statement that could work in both ways, that means it's a special statement? Well, yeah, that's a definition. So if you have a definition written in an if-then form, then its converse will still remain true. So if you have a definition, then its converse will still remain true. So in this case, remember the converse means you're going to exchange or flip the hypothesis and conclusion. So in this case, if two lines intersect to form a right angle, then they are perpendicular. We can flip this part with this part. Since the definition, it will still remain true. If two angles are perpendicular lines, then they intersect to form a right angle. So that still checks out because it's a definition. So that's that special kind of statement that you would be able to say the converse is true. All right, so why are we doing all this? Why are we talking about logic? Well, really because we want to figure out different conclusions in geometry, and we need to explain how we got there. We need to use logic to explain how we got from step 1 to step 2 to step 3. So here I want to talk about deciding whether each statement about a diagram is true. So is this true? And why? That's what I want us to do here. So the angle AEB and angle CEB are a linear pair. So we have AEB and angle CEB. Are they a linear pair? Thinking back to our definition of a linear pair, that means that they share a side and the unshared side is an opposite ray. So is this a linear pair? Yes. Because we know that these two have a non-common side, because the non-common sides are opposite rays. There's lots of different ways that you could explain this, but you would say yes, and this is why. That's why we need that logic. We need to be able to explain why. This next one says EA, ray EA, and ray EB are opposite rays. Is that true from this picture? We have EA and EB. Is this true? No. Because they're going in different directions. The rays are not opposite rays. E doesn't even lie on the same line as AB. So if you had AB going like this, with E here, that would work, but that's not what we got in this case. They're not going in the same direction. So this is just to show you that that's why we're using this logic, to be able to figure out if we can conclude different things and back it up. Just like in other subjects, when you have to use context clues or talk about where you found it in the text, here you have to give a reason as to why did you come up with that. All right, a biconditional statement. A biconditional statement is a statement that contains the words if and only if. If and only if. So this is a really kind of special statement. Any valid definition can be written as a biconditional statement. So that means you need an if and only if. So let's talk about an example. Write the definition of perpendicular lines as a biconditional statement. So, our definition is if two lines intersect to form a right angle, then they are perpendicular. What's the converse of this? Because it's a definition, right? We talked about how a definition can be written in the converse and it will still be true. So, that means if two lines are perpendicular, just abbreviating there, perpendicular. So I'm taking the conclusion and flipping it with the hypothesis. If two lines are perpendicular, then they intersect to form a right angle. Then they intersect to form a right angle. Since it's a definition, the converse is also true, because a definition is a really special kind of statement. So both of those are true. If two lines intersect to form a right angle, then they are perpendicular. If two lines are perpendicular, then they intersect to form a right angle. Now what about a biconditional statement? We can write valid definitions as biconditional statements. So two lines are perpendicular. Two lines are perpendicular, I'm abbreviating. Here's the key. If and only if and only if they intersect to form a right angle. So whenever you see an if and only if, that means that you can write it both ways. It's a definition. You could write it as a regular definition, an if-then. You could write it as its converse, flip the hypothesis and the conclusion. You can also write it as a biconditional statement. Two lines are perpendicular if and only if they intersect to form a right angle. It also works as two lines intersect to form a right angle if and only if they're perpendicular. That's why definitions are so special. They're really special statements.